In this video, we're going to get our third definition for sine and cosine. So we're going to have these three different ways of conceptualizing a sine and cosine. They won't contradict each other ever, but they will just, each of them give us sometimes a more efficient way of thinking about it and answering questions. So our first one was the one you learned way back in your geometry days. We call it the SOHCAHTOA, or the right triangle definition, where in a right triangle we know that the sine is the opposite over the hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And that's great, but it's limited because you have to have a physical right triangle. From there, we moved to the unit circle definition, it's called, where we imagine a circle of radius 1 centered at the origin. And in that definition, we can say that the sine and the cosine are the y and the x coordinates of the point where the terminal side of our angle intersects the unit circle. And then we can get the tangent from that sine and cosine, that the tangent is the sine divided by the cosine. Now, the third definition is kind of a combination or a hybrid of the two. So we're going to kind of think of it as a right triangle, but really as coming from a circle with any radius. So I've drawn here, the yellow circle is a unit circle, and the green circle is a circle with any radius r. The blue angle, the terminal side is the blue, and you can see the little red theta in there. So if we look at, say, a right triangle here that is formed by dropping that perpendicular down to the x-axis, and we're thinking of x and y as the coordinates of the point on the circle of radius r where the terminal side of that angle intersects it. Then in that right triangle, we've got our angle theta is here, we've got x and r, and then the hypotenuse is the radius of the circle, which is r. So we get the cosine of theta is going to be x over r, and the sine of theta is going to be y over r, and we can still do the tangent of theta either way, just as y over x, or probably that's going to be the best way to do it. We could also think of it as sine over cosine. So the difference here from our right triangle definition is that now the x and the y that we see here are not really the physical side lengths on this triangle. They are the x and the y that are the coordinates of the point on the circle. So that's saying that we could take an angle in any quadrant. So if we took our angle over here and we used the x and the y coordinates of that point on the circle, notice now that because we're in quadrant 2 where I've drawn this, that x value is going to be a negative. So now as we draw our triangle, this x is going to be a negative, this is a y, our hypotenuse is always going to be positive. So because the x and the y that we're using in our definition come from the x and y coordinates on the circle, not necessarily like in our SOHCAHTOA from an actual triangle where it wouldn't make sense to talk about side lengths being negative. It's going to expand our understanding of sine and cosine. So let's scroll down and see how it's going to work in practice. So we are going to say the terminal side of an angle contains the point -4, -1. Can we find the exact value of sine, cosine, and tangent? So here's our xy axis, and we're going to go to -4 on the x. 1, 2, 3, 4. -1 on the y. Here's our point there. Now, there's kind of, you can imagine there's a circle kind of in the background, but we aren't really going to draw the circle. We're going to draw that, we're going to call this a reference triangle. So the triangle that goes all ways perpendicular to the nearest x-axis is a reference triangle, just as we've talked about the reference angle. So it has to go to the x-axis. Do not draw it to the y-axis. Now, this theta that we call here is going to have the same sine, cosine, tangent of this actual angle here when we put our side lengths as having the correct plus or minus sign based on where the coordinates of those points are on the circle containing that point. So that's a long-winded way to say that we're just going to label our signs and allow them to be negative. Now, the hypotenuse is always positive 100% of the time, and that's just Pythagorean, so we're going to get that square root of, 4 squared plus 1 squared, that's the square root of 17. So our hypotenuse is the square root of 17. So our exact value for sine cosine theta is now just like our SOHCAHTOA, only we've allowed in this new idea, this new concept of sine cosine tangent, for the side lengths to be negative. So the opposite is going to be negative 1 over the square root of 17, and we'll be expected to rationalize that and make it into negative square root of 17 over 17. The cosine of theta will be the adjacent, negative 4 over the hypotenuse square root of 17, and we'll rationalize that as well. And the tangent of theta is going to be opposite over adjacent, which is going to be a negative 1 over negative 4, which is just 1/4. Okay? Let's do the same idea with negative 2, 3. So in this case, we're going to put the x's at negative 2, the y at 3. So here is our reference triangle. We'll label the side lengths and include the sign, positive or negative, depending on what the coordinates are. We'll find the hypotenuse using Pythagorean theorem. So that radius of that circle is going to be the square root of 13. And so then we'll get the sine of theta is going to be the opposite. And our angle is always going to be this angle closest to the origin. So it's always this angle right in here. So the opposite is going to be 3 over the square root of 13, which we'll rationalize and call 3 square root of 13 over 13. The cosine of theta will be the adjacent. See how we pick up that negative value because its x-coordinate is negative. And so as we know, cosine is negative in quadrant 2, and the tangent of theta is going to be just opposite over adjacent, and that's going to be a negative 3/2. Okay? Now we're going to go to another really important idea here. So there are some values for sine, cosine, and eventually we'll add in tangent and other angles, but particularly for sine and cosine, that just come up so often that we're going to need to know them by memory, which seems really daunting at first, but I'll try to explain how we can kind of think about this logically. So we want to eventually just know off the top of our heads what the sine and cosine of 0, 30, 45, 60, 90, and any other multiple of that. So if I said, what's the sine of 225 or the cosine of 330, or eventually we'll get to the tangent of a negative 210 degrees, it's something that we can come up with in a matter of a few seconds. So let's see where these come from. They're going to involve using our special triangles. So let's remember our special triangles here. So when we have a 30, 60, 90 triangle, we know the side lengths go x is the short side is opposite the 30. The x squared of 3 is the long leg opposite the 60. And the 2x is the hypotenuse opposite the 90-degree angle. So the idea is if you look at here is, I'm going to draw these here. So this would be a 0-degree angle. This is going to be a 30-degree angle. We'll get a 45-degree angle, and then we'll get a 60-degree angle, and then we'll be back up to a 90-degree angle. So we're going to concentrate first here on quadrant 1. If we can learn these, then we'll be able to figure out what the others are just by adjusting, looking at the reference angle, and deciding is it a positive or negative quadrant for sine and cosine. So let's do first, say, the sine of 30 degrees. And so we know in a 30, 60, 90, here's our 30-degree angle. It's going to be the opposite, which is x, over the hypotenuse, which is 2x, and so that's 1/2. So what that's saying is that the sine of 30 degrees is 1/2, always. It's a characteristic of that angle, of that 30-degree angle, that its sine is 1/2. Now, we can also do, since we have this triangle here, let's get the cosine of 30 degrees. And so that's going to be the adjacent over the hypotenuse. So for that 30-degree angle, that's x squared of 3 over 2x. The x's cancel, and we'll get square root of 3 over 2. So the cosine of 30 degrees is the square root of 3 over 2. Now, in this triangle, we can also do the sine of 60 degrees. So looking at the 60-degree angle, opposite over hypotenuse is going to be exactly the same as we got for the cosine of 30. Remember, we said that these are called cofunctions. The sine of one angle is the cosine of its complement. So if the cosine of 30 degrees is square root of 3 over 2, the sine of 90 minus 30, which is 60, should also be square root of 3 over 2, and it is. And likewise, we can do the cosine of 60, and you may be able to predict this, that that's going to be, for our 60-degree angle, it's going to be the adjacent over the hypotenuse, which is the same thing we got for the sine of 30. So the cosine of 60 is 1/2. Now we know that at 0 degrees, since that's a unit circle, it's the coordinates of that point is 1, 0. The cosine of 0 degrees is the x-coordinate of that point, and the sine of 0 degrees is the y-coordinate of that point. Let's look at the 45, 45, 90. If we look at a 45, 45, 90 triangle, then we remember that the side lengths go x, x, and x times the square root of 2. So the cosine of 45 degrees, I'm going to look at this 45-degree angle here, is the adjacent over the hypotenuse, which is 1 over square root of 2, and after we rationalize that, that's going to be the square root of 2 over 2. So the cosine of 45 degrees is square root of 2 over 2. But you can see that the sine of 45 degrees is exactly the same thing. And so this is kind of nice because it makes it an easy place to kind of reset or check. At 45 degrees, sine and cosine are the same. They're both square root of 2 over 2. Now at 90 degrees, we're up here, and we know the coordinates of that point are 0, 1. So the sine of 90 degrees is the y-coordinate of that point, and the cosine of 90 degrees is the x-coordinate of that point. Now, here's the idea behind it. This looks really daunting, but in fact, I'm going to do just a quadrant 1 for now. This is pretty easy, I think. You can remember this easily if you kind of think of how you're going to progress, that there's an ordering to this. So I'm going to put these angles in. So, and I'll do this in class, and I'll do it visually by showing my arm moving up. But our angle is 0 degrees, this is 30 degrees, this is 45 degrees, this is 60 degrees, and this is 90 degrees. So as we work our way from small to big, and we look at the values of sine of theta, you can see that they get progressively bigger. They start small, as they should, because remember, the y-coordinate at this point is going to be the smallest. This, if we're imagining our unit circle, is going to have a little bigger y-coordinate, a little bigger still, biggest it can possibly be. So these values are going to go in order from smallest to biggest. 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. Just 5 values that you have to know. 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. Cosine is the x value, so it starts the furthest out we can. It starts big. And then it progressively gets smaller because as we move along the circle, those x values get smaller and smaller. So it starts as big as possible and goes down. 1, square root of 3 over 2, square root of 2 over 2, 1/2, 0. The same 5 values, the same 5 numbers, just in reverse order. And so if we were going to, if, I didn't have the chart there, and I said, well, what is the sine of 60 degrees? You would have a mental picture in your head, and you would go, there's 0, 30, 45, 60. So 1, 2, 3, 4 clicks. Sine starts small, so you're going to go in order 0, 1/2, square root of 2 over 2, square root of 3 over 2. There we have it. Sine of 60 degrees is the square root of 3 over 2. Okay? Well, we'll practice this some more, but this is one you're going to have to memorize and learn. Once we can get quadrant 1 down pat, then it's not hard to get the others. And that's what I'm going to talk about here in this one. So if we're trying to talk about the coordinates of a point on a circle with radius 6, centered at the origin at an angle of theta equals 150 degrees. So we have our circle, it's got radius 5, our angle's at 150 degrees. Now we said with our new definition that the cosine of theta is going to be x over r, and that means if we solve for x, it's going to be r cosine theta. We know the r is 6, and our theta is 150 degrees. Now here's kind of a preview of where we're going once we can master this part of the table that's in quadrant 1. We can look at the reference angle for 150 degrees. So 180 minus 150 is 30 degrees. So that is our reference angle. Now we're going to know the cosine of 30 degrees. We're going to learn from memory. And we're going to think, well, let's see, cosine, we're going to go 30 degrees. 0 is the first one. 30 is going to be the next angle up. And we know cosine is going to start big, so it's going to be 1 at 0, and then we're going to go down, and the next smallest one is square root of 3 over 2. So we know that the cosine of 30 degrees is the square root of 3 over 2. We're going to do all this from memory. Then we'll say 150 degrees is in quadrant 2. In quadrant 2, the x-coordinate of any point is going to be negative. So we know the cosine of 30 is square root of 3 over 2, which means the cosine of 150 is negative square root of 3 over 2. So then, answering the question, we know that the x-coordinate of that point on a circle with radius 6 centered at the origin for an angle of theta equals 150 is going to be 6 times that negative square root of 3 over 2. We'll cancel the 2 and multiply and get negative 3 square root of 3. That's the x-coordinate of that point on that circle. All right, this will take some practice, but we'll get it.